Okay, so thank you, Hoang. And Hoang gonna give a talk today on optimal conversion rate for homogenization of convex Hamilton-Jacobi equations in the spatial temporal environment. Please.
Okay, so may I start now?
Yes.
Okay. Okay. Um, Today I would like to present a little bit on the main result of my senior thesis, which is on the optimal conversion rate for homogenization of convex Hamilton-Jacobi equations in the periodic spatial temporal environment. This is an interesting question, which Professor Hung has suggested me in December 2021, and it took me about a year to finish this properly. And first of all, I would like to present that why do we consider Hamilton-Jacobi equations? We know that, for example, there's a lot of problem in mechanics or in reality which could be formulated by a partial differential equation, and especially in mechanics, this is a place that we see many Hamilton-Jacobi equation arises. For example, you could imagine that we have a surface in the space, and uxt is a smooth function, and if we denote the zero level set of uxt by gamma t, and gamma t is our surfaces, and we want to study how the surface evolve when the time varies. And for example, we could assume that this surface is smooth and closed, and the equation describing the from propagation of the family of surface is ut plus ax du equal to 0 in Rn times 0 to infinity. This is quite simple to derive this equation, but we could see that we get an equation which contains the derivative of the function with respect to the time variable and some term ax du here, and in general, we may replace this term by a function h, and we will call it Hamiltonian. To study about the Hamilton-Jacobi equation, one of the main difficulty is the Hamiltonian is generally not a linear function. So sometimes to get the well-posedness of the problem, or the uniqueness of the solution, or some further properties like smoothness, it is a little bit quite difficult. So we have to find some other ways to get informations on the solutions of the partial differential equation. One of the most common method is to consider the homogenization. That you could imagine something like that. Instead of considering our equation, we could fluctuate it a little bit to get a kind of approximate solution, and then we try to study how close that approximate solution to our solutions of the considered equations. For example, here I will consider the Hamiltonian HXTP, which is smooth, and it is also convex in P, and we have a further assumption that it is periodic with respect to the spatial variable x and the time variable t. And moreover, it also satisfies a condition of growth rate, which is the growth rate of h is bounded above and below by a function of p, the m0 power of p for some positive constant here. Normally, when Professor Nguyen-Tien and Professor Yu consider this equation, when the Hamiltonian is time independent, they did not need this condition, since they can always assume that the Hamiltonian has a quadratic row. But in this case, because of some constraint, we cannot do that. And for each positive of epsilon, I will let u epsilon be a unique viscosity solution of the following Hamilton-Jacobi equation. And if we let the epsilon variable, it tends to 0. Normally we understand that u epsilon will converge to some function u, but how it is, and the function u, it will satisfy a partial differential equation like this, where the h bar is called effective Hamiltonian. And this property is proved in an article by Evans and Gomez in 2002. So for where the h bar is defined as following: for each p in Rn, there is a unique constant hp such that Vs plus hy sp plus dv equal to h bar p has a continuous viscosity solution. V is often called corrector because, okay, I will explain it later. But to get some intuitive imagination on this situation, I will provide you a heuristic example. Of course, here the Hamiltonian is not time dependent, but if we consider again the first order propagation problem like above, which is u epsilon t plus a x over epsilon d, here should be the u epsilon is equal to 0 in Rn and with positive time. You may see that the okay, I will zoom in a little bit. Okay, the dot here is the viscosity solution for each bar epsilon, and if we let epsilon goes to 0, it will converge to some function, orange function here, which is like the average behavior of the families of u epsilon. And then okay, and then here we expand if we expand the u epsilon with respect to u and the epsilon variable here, will you get some approximation like this? Of course, I'm assuming that everything is fine now. So that's why we call the function v here is corrector. And obviously, if the v is bounded by a constant, then we will know that u epsilon will converge to with the O epsilon conversion rate. So the very fundamental question here is how fast does u epsilon converge to u when epsilon goes to 0? Normally we don't have the boundedness of v, and we don't even have some uniqueness or smoothness of u as usual situation. So because we can guess O epsilon is the right conversion rate, it is quite hopeless to verify that rigorously for a general equation. The best conversion rate, which is obtained for even non-convex Hamiltonian, it is get by Capuzzo, and Ishii in 2001. That is O epsilon power to 1/3. It could be improved to epsilon power to 1.5, but it we also need some unrealistic conditions on the diffusivity of the solution or something like that. I don't remember so well, but oh, sorry. But of course, it is quite difficult. So one of the best thing to do is just first consider the problem for the convex Hamiltonian. And because when we get convex Hamiltonian, we will get some better estimation, and which is more convenient to obtain our result. For example, in an article of Mita K in 2019, he pointed out that the lower bound is optimal, which means there exists a universal constant C only depends on H, and the norm of G in L infinity such that U epsilon minus U is not less than C epsilon. Also, the optimal conversion rate holds for low dimensions such as 1 or 2 dimension. In greater dimension, it is a completely different story. Kopperman in 2022, he only showed that by using idea from first passage percolation method, he obtained an upper bound, and he get that the difference of U epsilon and UU is bound by a function which is depends on t with a log term here, logarithm term here, but we had also get C epsilon here. And the Tyson in 2021, when he considered the one-dimensional multi-scale setting, he also get the conversion rate O epsilon. So naturally, we would think this would be true, and indeed, in December 2021, Professor Chen and Yu had completed the success in show that the optimal conversion rate must be O epsilon for arbitrary dimension when the Hamiltonian is time independent. So naturally, we will try to consider this problem for time dependent Hamiltonian, and we will try to discover that which is our difficulties here and how to overcome that. So that was the main work of my thesis, and it is true also. In the given equation, if we assume that the initial data G is the Lipschitz function, then we also get this O epsilon of conversion rate. So the key ideas here is I just reuse the optimal control formula, which is stated in an article of Evans and Gomez, also in articles of Professor Chen and Professor Yu, and a nice lemma on the composition of continuous curve by Burago in 1992. But what makes the difference here? Because if you read the paper of Professor Chen and Yu seriously, you will see that they will try to express the viscosity solution in the form of the minimizer, and which is quite geometric, and they try to cut into glue the minimizer together. But by the they will use also the periodicity to do it. But in this situation, we must be extremely careful when we try to do the same task, because here we also get the periodicity in time variable, so we cannot shift them arbitrarily to glue the endpoints together, and I will show that in later. Okay, so we get here the optimal control formula for the solution, which is quite not so easy but not so hard to prove. You have to modify it just a little bit from the things that was done for the convex for the time independent case, and then the MTXY, I will call that the homogenized metric, because you may imagine that is the minimum cost of the Lagrangian L when the eta is an absolute continuous curve defined on the 0t, which has two fixed endpoint at eta 0 is x and eta t is y. And L bar, that is the Lagrangian of H bar, and it could be expressed also by a function depends on the homogenized metric. So the essential part of this essential part. Hello?
Yeah.
Yeah.
Can you go back to the previous one, and maybe can you draw some pictures explaining a bit more on the optimal control formula? Because yeah, I mean, not everyone is an expert.
Okay.
In this.
Okay. So a minute, please.
Yeah.
You see my bar here?
Yes, I do. Yeah.
Okay. You may imagine the optimal control formula like that. Here we have x and y. Yeah. And the optimal control formula is like that the solution could be expressed by a function by mtxy. Here either this is an absolute continuous curve defined on 0t and Rn, and two endpoints are fixed. For example, like that, this is another curve with the that curve is the curve makes the cost become minimized. We will call it the minimizer later, and we will base on this interpretation to try to get the optimal conversion rate by some estimation on this. Okay, I will note that we get m bar. That is the limit when k go to infinity of 1 over k m kt kx ky. Okay. Okay. Here are two lemmas to get that. First, it is easy to show that the metric m is the n periodic. It means that if you shift to n points in the space, which such that they shift it by an integer vector, then the metric is unchanged. But then we need to estimation on m, that is the subadditivity and superadditivity. I would write it here for convenience of people. First, we will need that is subadditivity, which is m2t 0 to y. That is not smaller than 2m t0y plus a universal constant c. That is the subadditivity.
You mean less than or equals to, right?
Yeah, less than equal to. Okay. And later we will need a superadditivity property. We just reverse this inequality, which is m2t 0 to y is not smaller than 2mt0y plus a universal constancy. Okay. This is simple, but this is a little bit much more complicated, and to prove the superadditivity, I think that I have made some observation which is quite different from the method of John and Yu. Okay, for the superadditivity, because we want to get the m from 0 from 2y in the time of 2t, which is bound above by 2mt0t, we will think that, okay, we will patching trace of the mt0y and we shipping them in an appropriate way. Here you could see that we have two black curve here, and then we want to shift them together, but we cannot glue their endpoints. So we just shift them as close as possible to create a connector from y to y minus w here, and then the another endpoint will be to y minus w, and then we connect it to y. But because we must use connectors, we should save a little bit time for it. And here we will, on the red part, I will point out that there exists a red part which we can move faster on that part, because if we regard the dot eta dot like the velocity of the curve, we will move faster there, and then we will save some time for the connector. In the time-independent case, Professor Chen and Yu initially they must use the property that the velocity is uniformly boundedness. But actually, we don't need that. We just need the boundedness of velocity on an appropriate segment, because when we have an estimation like this, could you see my board now? T eta t, we may get a kind of estimation like this. It is bounded above by ct. Hence, there exists an interval L to L plus 1. Or I could replace 1 by some constant, which is because of my choice, such that the velocity of eta naught to the power of m from L to L plus 1 is bounded both. Yeah, and then I will consider a path on the red segment for something like this. It means eta 1t, which could be used to a eta t plus some constant vector b here, and by computing the velocity, we will get that the velocity on this new curve is 8 times of the initial curve. But if we plug it in here, it also be bounded by the constant, so everything will be okay.
Can you also
but for
explain?
the super
Yeah, so this is surely also clear to me or someone who has been working on this. Can you also explain
Okay.
like what is the vector W? I mean, your picture is clear when you do shifting, right? Maybe you can
Yes.
explain what is the vector W in your in that slide of subadditivity. Thank you.
Okay. So for people's convenience, I will draw two copies of MT0Y here. I have two copies of it here, and I want to shift that to patch the endpoint together to get a path from 0 to Y. But because of the periodicity, we could not match the endpoint Y to 0 here. So it should be Y minus W, where Y and Y minus W, it lies, oh, no S here, in the same unit curve. And here W is an integer vector. We could always do that because our space could be partitioned into unit curve. So we could also choose an appropriate W such that Y and Y minus W lie in the same unit curve. Okay, and then we just connect them like this because they lie in the same unit curve. The distance is about at most square root of m square root of n here minus W and Y. The distance between them is at most square root of n. And if I choose the velocity, I just save the time for about 1 or 2 for this segment. I will get that in this connector we will also get bounded cost here. Is it okay? And for another endpoint, we will get another endpoint here. It's 2y minus W, and for here is 2y, and it's also get bounded both. So we will get a picture like this, 0 to y, but then we connect it to y minus W, to y minus W, and connect it again one more times to 2y. And here is the it's a part of the curve which we must move faster to save some time for two green connectors, and we need the boundedness of velocity here. Okay. Okay. The detail is a little bit quite nasty. It requires some calculation, and there will also be some problem on that calculation, which I'm also thinking about. I will tell it to you at the end of this talk. Okay, for the super additivity, this is another big problem because this is quite simple for us to patch to a trace from together to form a longer curve. We could imagine that, but how about when we get a curve from 0 to 2y? How can we divide it to some segment or to subcurve to get some copies of MT0y? This is quite unrealistic if we want to choose some point to cut it up by 2 parts. So here we must use a lemma by Burago. That is okay. You could see a statement here. Let n be a positive integer and zeta be a continuous part. And there's a positive integer and a collection of disjoint subinterval satisfying the difference of those interval is exactly half of the interval, half of the displacement, initial displacement. You can see it like this. Here is zeta 0 and here's zeta 1. I could choose some I could choose some subcurve like that. Here is a zeta AI, zeta BI, such that the sum of zeta BI minus zeta AI is essentially half of the initial displacement. Okay, so I will use this to cut the minimizer of the M to T0 to Y into some parts, satisfying the half of the displacement like that. But I want to also cut it in a time variable. So if I consider eta 1 t is eta t and t, then I can cut it to some parts such that sum of eta bi minus eta ai is y, and sum of bi minus ai is t. Now the rest is to glue them together. But there will be another problem here. To form a new curve from 0 to I, generally we could not directly gluing them, but shifting them as close as possible in every variable, as we see before, that is a worse idea since the velocity of connector might blow up. Okay, so I will explain why it could blow up here, because for example, if you get here is at the AI, BI, and here is AI plus 1. If those endpoints are close enough, then because the velocity is velocity is the distance over the time, yeah. And if we shift the time variable close enough, for example, the time difference is AI plus 1 minus BI, which is approximate to 0, then the velocity will blow up, and we could not effectively compute the cost here. So the main idea here is to shift those subcurves as close as possible in spatial variable, but we have to let it a little bit distant in time variable. So we inductively define Ci and Bi like this, such that we preserve the distance between Ai and Bi, but the distance between Bi and Ai plus 1, which will be transferred to Bi and Ci plus 1, we will let it lie between 1 and 2. This is possible because we can choose appropriate integer vector to shift it like that. And now here we just need some connectors to connect the 0 to the first endpoint, which had the time is C1, and then the next connector to connect the points of at the time D1 to C2, and so it happens like that. And here's the decay to the point to another point, that is Y. Because we will save time for connector, and we have fortunately an exact number of connector, which is about both by n or n over 2, something like that. So here's the picture. You could see that we connect 0 to zeta C1, connect, and we have to rescale a segment on the zeta C on some subcurve like that. But because we have a lot of segment, so in this case, I only consider when the time t is large enough, so that I could spend time effectively for those connectors like that. And that is the end of my talk. The rest is just calculation. So maybe that's all I want to present today. About the problem I've mentioned before. Because you see that initially we have a quite strange condition on the Hamiltonian, that is alpha pm minus c xtp not greater than beta pm plus c. Because in my calculation, I heavily depends on the fact that the upper bound and the low bound and the upper bound are mth power. I'm trying to do this a little bit more generalized. For example, here should be M1 and here should be M2, or M1 smaller than M2. But at the moment, if I try to do that, there will be some problem when I consider the boundedness of some part of the curve, and I cannot proceed calculation. So maybe to improve this to M1 and M2, we should find how either a more clever estimation or another method. Yeah, that's all.
Okay. Yeah, because you still have time, so maybe let me ask you two questions so that you can explain
Yes.
better to the audience. Like the first thing you do say about the fact that you need to have a bit of time, which is
Yes.
very different from the time independent case. So can you explain that a bit clearer? Of course, you have the earlier picture, right? But can you draw and sort of explain it a bit clearer? On that.
You mean this?
Yeah.
You mean this picture?
Yeah, because again, I mean, it looks a little bit cryptic, right? I mean, like, so you did explain that you would need when you do the cut, you move the pieces together, and you need time, right? Can you explain that clearer?
Okay, I will explain that. I recall that we have some sub-segment of the curve is zeta AI and zeta BI, like that. Zeta AJ, zeta DJ. And because we want to connect them together, so ideally, if we want to save the cost for the connector, we must move the endpoint as close as possible. So in spatial variable, we could easily do that, like this. No, I will try to do like this. But how about the time we use for this connector? If we use the time is the difference in the time for the connector is AJ minus BI. If we just shift it naively, but if it is approximate to 0, for example 0, 0.1 or 0.001, and we just consider a naive straight path from the U to V, like V plus S over C V minus U. If we just simply consider this naive path, because I will connect them by straight path, and the velocity would be V minus U over T, where T here is the time difference between two endpoints. And if this is close to 0, then the velocity just simply blow up. So I have to set them a little bit distance, which mean I will shift them. For example, here is A1, B1, A2, B2. Yeah, and so it like that. I will shift them by integer vector to an interval C1, D1. But here, C2, D2, we satisfy C2 minus D1 greater than 1 but smaller than 2. Yeah, and it happens like similarly to other time interval. That's why we have to inductively define Ci and Di, because if we have a choice for C1 and D1, and then we choose C2 and D2, so Ck and Dk. The time we use for the connector is about 1 to 2 for each connector is about 2k, from k to 2k. Yeah, it is also computable from our constants such as n. So we could easily compute it without worry that it would blow up. Not depends only on our constant.
And for experts in the audience, of course, so the second question, and then we can do more informal chat after this, is that for experts in the audience, people know that for the time-dependent equations, then it's impossible to get uniform Lipschitz estimates or things like that. And hence you need to assume that for now, the Hamiltonian grows with exactly the same power, right? And you did explain that maybe, but you haven't sort of explained what was the crucial point that you need to use that the Hamiltonian or Lagrangian that grow of this exact same power. Can you explain that to end your talk?
Okay. So I have already assumed that they grow in the same power like this. B P M plus C. Because as in the subadditivity case, I want to get some interval for example L to M plus M, such that the velocity on this interval is bounded eta S eta dot S C. Because of this estimation, I could derive something like eta integral of eta S M minus C here. Here we take the integral from L to L, to L plus M. And from that we get
Probably
the velocity on
at the dot, right? And to the power M prime, which is the dual of M.
Prime. Yes, M prime to the dual of M.
Mm-hmm.
It's bounded above by the constant. Yeah, so I get it. What happened if I consider M1 and M2 instead of the same power of M? If we get the M1, we will get here L to L plus M. The power here must be replaced by M1. But for the shifting shifting process, for example, we go faster on some part of curve. If we get some eta 1 S is a eta S plus B on L plus M. Here A and B are some constant. By shifting that, we will see that the L eta 1 S eta 1 dot S here on L2 plus M. We want to estimate the cost here for the path eta 1, and we will also want to show that this is not so much different from the path eta S. And if we naively use the velocity bound here, we could only get is bounded above by some term which has M2 power. And the boundedness of the velocity in M1 power does not guarantee that we will have this boundedness for the M2 power here. Here, question mark here. We're not sure that this is bounded by a constant. So if we just use the same techniques, it just simply does not work. So now I am having two directions to resolve this. One is I try to subdivide the bounded part for smaller and to use some theorem on measure theory, something like that. But it seems unapplicable too, so maybe we should find another direction, another approach to resolve this.
Okay, thank you. Are there any questions in the audience?
The question?
Yes, please, Hiro.
Yes.
So can you explain why you cannot deal with M equal 1?
Could you ask it once again? I could not hear so well.
The question is why you cannot deal with M equal 1. Or even
Why?
just simple, just the simplest case. So
M
you
equal 1.
explain the front propagation problem, right? So if you
Yes.
think A of x and t times
Yes.
the gradient u.
Yes.
Yeah,
Okay,
that's
this could not be used for m equals 1 because I think I have to show the calculation in my preprint for convenience of people. Fit with okay. M equal to 1. Okay. The problem why we cannot consider m equal to 1, that could write here when we take the integration.